This video will discuss the solution to question 26. Consider figure 2. What is approximately the equivalent capacitance of the internal node, that is at the gate of M2, which ultimately determines its time constant? So we are asked to determine the time constant at this node. However, there is still an important bit of missing information, namely the type of transistors that M1 and M2 are. But we can find this out with the information from the caption of the figure. It's given that the first stage is a common source amplifier stage and the second stage is a common drain output stage. That means that the source of this first transistor is connected to a constant voltage, so in this case the upper terminal here has to be the source, and for M2 the lower terminal has to be the drain. And this is only true when both transistors are PMOSes, so we can draw the arrows over here. Now we can go through each capacitance of the transistors and figure out if they contribute to the time constant of the internal node. So first, CGS of M1. That one is connected between the gates of M1 and the source of M1. It is in no way connected to the internal node and therefore it doesn't contribute to the time constant. CdB is the capacitance between the drain of the first transistor, so that is indeed connected to the internal node, and the bulk of the transistor. In this figure it's not given explicitly to which voltage the bulk is connected, but typically it's connected to a high voltage, so in this case VDD, for a PMOS transistor. So in a small signal equivalent, CdB is connected between the drain and a small signal ground, and therefore it contributes to the time constant of the internal node. CGD is connected between the input node here and the internal node. However, it is connected between two terminals of an inverting amplifier stage. So we might have to look at what happens with the Miller effect. We can compute that the equivalent voltage gain from input, so gate to drain, is approximately -100. However, we are looking at the capacitance from the other way around. We are looking at it from the drain to the input. And though there isn't any actual amplification, we can say that there is a ratio in amplitudes of the inverse of the voltage gain. So A inverse being 1/100 minus 1/100 is the ratio between the magnitude of the voltages at this internal node and the input node. If we now apply the Miller capacitance rule, so C equivalent seen from the drain here is equal to 1 plus the absolute gain seen from the drain to the other node, which in this case is the inverse of the normal voltage gain, which is -1/100, and that's multiplied by CGD. But 1/100 is much smaller than 1, so it's pretty safe to say that C equivalent is pretty much equivalent to CGD. So we can say that it contributes to the capacitance at this node by just a factor of 1 with respect to CGD, but it does contribute to this node. Now we can look at the capacitances of transistor M2. CGD is connected between this terminal and a ground here. So indeed it is a capacitance that contributes to the internal node. So we have to add CGD to it. CdB of the transistor is connected between the drain of the transistor and the bulk of the transistor. Since both of these terminals are not in any way connected to the internal node, CdB does not contribute at all to the equivalent capacitance in the internal node. The final capacitance we have to look at is CGS, which is connected between the internal node and the output node. And here it's a bit tricky because we are looking not at a common source configuration, but a common drain configuration where the gain is approximately 1. So the small signal that we put at the internal node is pretty much copied and Vout. In other words, there is not really a small signal voltage difference between the two terminals. So effectively, CGS doesn't hold any charge, and therefore it does not contribute to the equivalent capacitance in the internal node. So now we can make a final sum of all capacitances that contribute to the capacitance in the node. Those would be CGD of M1, that is 5 femtofarads, plus CdB of M1, which is another 5 femtofarads, and CGD of the second transistor, which would be another 5 femtofarads. So in the end, the total capacitance would be 15 femtofarads.